They'll have to come first. We don't have to start now. They'll come and then we'll start. We don't have to start now. वो लोग जब आएंगे ना उसके बाद स्टार्ट करना है. हाँ मैं रेडी होंगी. हाँ बता दूंगी मैं. Hello, good morning everyone.
Oh, she will call them. Okay. I was running to the stage, right? Yes, okay, that's fine.
Good morning, everyone. I am Sai Manigar, a research scholar from Agricultural and Food Engineering Department, IIT Kharagpur. It is my great pleasure and honor to be your host for this Gyan course, and I extend a warm welcome to one and all present here today. This is a momentous occasion and we are honored to have such distinguished guests with us. It is my privilege to welcome you all to this exciting course titled Characterization of Agricultural Particulate Materials for Effective Handling and Processing. First and foremost, I would like to extend a warm and heartfelt welcome to our chief guest, Professor P.S. Rao sir, our esteemed nominee of Head of the Department of Agricultural and Food Engineering Department, IIT Kharagpur. I now kindly request Professor Bhupendra Godki sir, Course Coordinator of Gyan Course, Assistant Professor, Agricultural and Food Engineering Department, IIT Kharagpur, to come up and present the bouquet to Professor Rao as a token of gratitude and respect. Thank you so much, sir, for gracing us with your presence today, and I will request you to please take your seat. Thank you, sir. Moving forward, I would now like to invite Professor Brajesh Kumar Panda, Course Coordinator of Gyan Course, Assistant Professor, Agricultural and Food Engineering Department, IIT Kharagpur, to extend a warm welcome to our distinguished international faculty, Professor Kingsley Ambrose. I kindly request you, sir, to please come up on the stage and present Professor Ambrose with a bouquet as a token of appreciation and admiration for his expertise and contributions to the field. Thank you so much, sir. I request you to please take the seat. As we continue with our program, it is my pleasure to acknowledge the incredible efforts and dedication that has gone into recognition in organizing this Gyan course. This course has been made possible by the hard work and commitment of 3 esteemed course coordinators. I kindly request them to introduce themselves to the audience in the following order. Professor Bhupendra Godki, Professor Brajesh Kumar Panda, Professor Praveen Kumar Sapatti. All of whom are assistant professors in the Agricultural and Food Engineering Department, IIT Kharagpur. Their relentless dedication, expertise and vision has been instrumental in bringing this event to fruition, and we are truly grateful for their contribution. Thank you to all of you, sir. Ladies and gentlemen, we have now reached a special moment in today's event, the lighting of the lamp, a traditional symbol of wisdom, knowledge, and the beginning of an enlightening journey. It is my honor to invite our esteemed dignitaries to perform this significant ceremony. I would like to request Professor P.S. Rao sir, our esteemed chief guest, Professor Kingsley Ambrose from Purdue University, Professor Godke, Professor Panda and Professor Sapatti, course coordinators, to kindly come forward and light the lamp. Thank you so much, dignitaries. This simple yet profound act marks the beginning of the Gyan course, and we are privileged to have such distinguished individuals here with us to bless this occasion. May the light of knowledge guide us throughout this course. Thank you so much to everyone present over here. It is now my privilege to invite Professor Bhupendra Godke to please come up and welcome the delegates and participants and share his valuable thoughts on the significance of this Gyan course and the importance of collaboration and knowledge exchange in shaping the future of agricultural and food engineering. Sir, the stage is yours.
Thank you, Ms. Saima. Respected dignitaries on the dais, Professor P.S. Rao, Professor Kingsley Ambrose, my faculty colleagues, beloved participants and friends, a very good morning to you all. I am pleased to welcome you to this unique 5-day Gyan course on characterization of agricultural particulate materials for effective handling and processing, which is scheduled from 16 to 20 December 2024 at Agricultural and Food Engineering Department, IIT Kharagpur. This course is funded by Ministry of Education, Government of India. The goal of this course is to familiarize participants with the properties and methods used to characterize the mechanical behavior of particles, powders and compacts, with the intention of using this property for process and performance design. The course includes lectures, laboratory classes and hands-on practical sessions, where you will have the chance to apply the learned concept directly. The participant will explore the techniques of particle size and size distribution, as well as advanced characterization methods such as X-ray diffraction, differential scanning calorimetry and dynamic light scattering techniques. Also, you will learn discrete element modeling, offering a detailed understanding of how simulations can enhance our knowledge of powder behavior. Overall, this course is designed to equip you with both theoretical knowledge and practical skills that can be applied in various research and industrial contexts. We encourage you to actively engage in this course and ask questions, and also explore the exciting possibilities. We hope this course serves as a valuable learning experience and fosters new insight into powder characterization and processing. Thanks to all for being here, and we look forward to an engaging and productive sessions ahead. Thanks to one and all.
Thank you, Professor Godke, for your valuable insights. It is now my honor to introduce you to our distinguished academician and researcher, Professor P.S. Rao, a leading figure in the field of agriculture and food engineering. Professor Rao's research has been pioneering with a major focus on non-thermal methods of food processing, which includes cutting-edge techniques such as high-pressure processing, light processing, ultrasound processing, membrane processing, to name a few. In addition to his academic endeavors, Professor Rao has also recognized the importance of translating research into real-world solutions. He has played a pivotal role in establishing the Agri-Food Business Incubation Center, a dedicated initiative that supports startups in the Agri-Food Business Incubation Center, a dedicated initiative that supports startups in agri-food processing. This incubation center, funded by Ministry of Agriculture and Farmers Welfare under the Rashtriya Krishi Vikas Yojana, is the first of its kind in the IIT system. We are privileged to have such a distinguished academician with us today, and I am certain that his insights will inspire all of us. Please join me in welcoming P.S. Rao sir to share his thoughts and experiences with us. Sir, the stage is yours.
Thank you so much, Saima, for such a nice introduction, though it's not required. So good morning, one and all present here. And it's my proud privilege and honor to be here and address this August gathering. So first of all, so warm welcome to Dr. Kingsley Ambrose, who is professor at Agricultural and Food Biological Engineering, Purdue University. He's a well-known figure, and of course, so he's known to me for a long time, and of course we met even very recently also in one of the ISA meetings at Parbani. And welcome, sir, and thank you for accepting our invitation. And I welcome all the participants who joined this program, so particularly from various places in India, and of course IIT Kharagpur as well. And before further moving, so I would like to just tell a little about this GAN, this global initiative for academic networks, which is termed as GAN, is a program or maybe a flagship program of Ministry of Education, Government of India. Basically, the aim of this GAN course is collaborate, innovate and educate. So with this concept, it has been placed for a long time, and of course it is a phase 3 probably which is going on. The program is designed basically to tap the talent pool of scientists internationally, to encourage their engagement with the Institute of Higher Learning, which are IITs, NITs, etc., so as to augment the country's existing academic resources, accelerate the pace of quality transformation, and elevate India's scientific and technological capabilities to global excellence. That is the main purpose. So GAN serves also as a platform for the exchange of knowledge and ideas on the global scale, and it enables institutes of higher education in India to invite and host internationally renowned academicians and researchers like Dr. Ambrose, and facilitating the co-teaching of advanced courses. So we of course earlier also conducted in this department some of the such advanced courses, and in the recent past this is one such a nice course. And for Indian students actually it will help in fostering collaborative relationships with the experts around the world. The program offers great opportunities for Indian students to closely interact with the international experts for a considerable duration. This at least we have 5 days in our hand to interact with Dr. Kingsley Ambrose. By participating in GYAN, students can gain invaluable insights, practical knowledge and of course international perspectives that enrich their academic pursuits and future careers. Furthermore, so thus all the students are requested to interact with Dr. Ambrose during the beyond the class periods, so that actually you can explore, so what further opportunities are there, so with Purdue University in general, maybe with Ambrose sir himself particularly. Furthermore, GYAN offers international experts a unique opportunity to familiarize themselves with India's academic environment. By interacting with local students and faculty, so you can explore the potential collaborations. It's not that only today actually Dr. Godke has invited, but all other young faculty also they can explore the further possibilities of any kind of collaboration. And as far as this course is concerned, the characterization of agricultural particulate materials for effective handling and processing is very important as such, and all of you must appreciate. So, understanding the material behavior is very important in designing any kind of handling systems, process or maybe even process technology, process lines as such. So, this is actually very vital in designing all these systems. Thus, the topic is very apt, and of course, I must appreciate the coordinators Dr. Bhupen Godke, Dr. Brajesh Panda and Dr. Praveen Sapati for their efforts in formulating this nice course and augmenting much valuable expertise of Dr. Ambrose. So, you have enough exposure during these 5 days. So, all of you will be having proper exposure of theoretical knowledge as well as practical demonstrations, and please utilize the opportunity to explore whatever the facilities the department is having particularly, and of course, those who are coming from outside, they can even visit our other facilities or maybe other what you can say establishments. Okay. And some of the faces looks new, so probably they are new to this department or maybe IIT. So, just I would like to tell briefly about our department. So, this department initially it was agriculture and food agriculture engineering and established in 1952, just after 1 year of IIT establishment. It is a very old as old as IIT Kharagpur, and subsequently in 1994, so giving a broader scope in the food engineering also. So, it has been renamed as agriculture and food engineering, and with 6 major disciplines as on today, and we are having formation and power, land and water resource engineering, food process engineering, aquaculture engineering, agriculture biotechnology and agriculture systems and management. However, our young faculty, they are engaged in particularly in food process engineering. So, we have actually many young talents these days, and they are engaged in wide variety of specialty areas. They are working in mechanized food processing, they are working in AI and ML domains and working with robots, working with process modeling, working with rural technologies for augmenting the small scale industries and valorization of byproducts, etc. And these are actually couple of areas not limited to. So, therefore, I urge all the faculty to facilitate Dr. Ambrose to show our existing facilities and laboratories and maybe interact very closely, so that further collaborations actually can be made. So, this is a great opportunity as such for us to give a real scenario of our strength to Dr. Ambrose, so that we can further collaborate in future. And of course, this department houses many unique facilities, which is one of that is Agri Business Incubation Foundation, supported by NABARD, and we are having this Center of Excellence in Artificial Intelligence and Food Nutrition, which is one of the new in its feather. And apart from that, actually one Student Activity Center, AC Pandya Student Activity Center, which is again supported by one of our illustrious alumnus, Dr. Vinod Gupta. So, these are the some of the major facilities. Apart from that, we have some model pilot plant facilities for FRK and ready to eat therapeutic foods, even vacuum frying, or such kind of facilities are there. And before concluding, I would like to say it is just a beginning. So, we have a long journey to perform, and coming together is beginning, working together is progress, and flourishing together is the success. So, let us supplement and complement each other's strength to build a meaningful collaboration with Purdue University and flourish jointly to meet the needs of the developing India. So, with these few words, I wish again the course a grand success, and thank the coordinators for inviting me and having me here on this stage. Thank you everyone, and have a nice time at Kharagpur and have a great learning. Thank you.
Thank you so much, Professor Rao, for your valuable words. Now, it is my pleasure to introduce our distinguished international faculty, Professor Kingsley Ambrose from Purdue University. Professor Ambrose, your expertise and experience are highly regarded, and we are privileged to have you here with us today. Dr. Kingsley Ambrose is a professor of agricultural and biological engineering and university faculty scholar at Purdue University, USA. Dr. Ambrose is a leading expert in agricultural, particle technology, grain processing, and modeling agricultural systems. At Purdue, he teaches physical properties of biomaterials, grain drying and storage, and characterization of particles, powders, and compacts. Dr. Ambrose leads the renowned Agricultural Particulates Laboratory at Purdue and is also a part of Purdue's Center for Particulate Products and Processes, CP3. In addition, he oversees the CP3's Characterization Laboratory. His research interests are in particle technology, particle modeling, particle design, milling, and grain processing, bulk material handling, and dust explosion prevention. Dr. Ambrose has been the principal investigator, co-principal investigator of projects funded by US Department of Agriculture, US Department of Labor, US Department of Energy, and various private companies. He has authored, co-authored more than 110 peer-reviewed journal articles, 4 book chapters, and more than 140 conference presentations. He is also co-investor for 3 US patents, 1 US patent disclosure, and 1 Indian patent. He has given invited talks in US, UK, India, Italy, Brazil, China, Oman, Mexico, and Singapore. Nevertheless, academic and professional community service is an integral part of Dr. Ambrose's discovery and educational activities. Since 2013, Dr. Ambrose has trained more than 1,100 grain handling and industry workers on methods of preventing grain dust explosion. Dr. Ambrose is actively involved in professional societies and is holding or has held a variety of leadership positions. He is an associate editor of American Society of Agricultural and Biological Engineer Journal and serves on the editorial board of Journal of Cereals and Oilseeds. Dr. Ambrose serves as a permanent guest member of the Working Party on Mechanics of Particulate Solids, European Federation of Chemical Engineering. Moreover, he is a recipient of many esteemed awards. To name a few, he is a Fulbright Scholar Awardee. He has received the Outstanding Reviewer Asabe Processing Systems Award. Further, he has also been awarded as the best scientist at ICAR, CIFET, and many more. I kindly request you, sir, to please come up and share some words with us.
Thank you for the nice introduction. You all can hear me okay? Yeah, okay, thanks. Good morning all. Morning, right? So hopefully this is Monday morning, right? So it's still waking up, right? But again, I'll be talking for next 4 days, so I'll not, take much time. Again, thanks for, nice introduction. First of all, thanks to Dr. Gotke, who, contacted me, reached out and, proposed this program. I thought this will be a wonderful opportunity for me to visit here, teach, and also interact with you all. So a couple of things, as both Dr. Gotke and Dr. Rao said, I love to interact. Sometimes my students and my kids say I talk a lot. But I love to interact. So feel free to ask me lots of questions, and I will also look forward to learn about your research, your other career goals, etc., etc. Okay, whatever I can contribute or whatever I can suggest you to. Okay, that's it. Again, you will be listening to me for next 4 days. So again, thank you all, and looking forward to learning more about you all. Okay, thank you. Yeah.
Thank you so much, sir. We are thrilled to have you here with us, and we look forward to the invaluable knowledge and perspectives you will share, sir. Thank you again. As we come to the end of our welcoming session, I would like to invite Professor Praveen Kumar Sapatti to deliver the vote of thanks and express gratitude to all those who have been able to make this event possible.
Thank you, Saima. Good morning, everyone. As we come to the conclusion of this inaugural event, it is my great pleasure to stand here today and express my gratitude to everyone who is making this Gyan course at the Department of Agriculture and Food Engineering, IIT Kharagpur a success. Firstly, I sincerely thank our Director, Professor V.K. Tiwari, and Deputy Director, Professor Rintu Banerjee, for their constant support, guidance, leadership, and encouragement which are making this event possible. Secondly, I thank our head of the department for his vision and effort in bringing this event together. I would also like to thank Professor Rao. He is extremely busy, and thank you for making out time to be in our inaugural as a patron for this event. I also appreciate Professor Kingsley for playing a key and significant role in ensuring the smooth running of this course. We are also especially grateful to Professor Anil from IIT Hyderabad, who is also National Coordinator from the Ministry of Education, for sharing his knowledge and expertise with us and helping bring experts and participants together for this course. We would also like to thank Professor Hemanti Banerjee, Associate Dean CE&T, IIT Kharagpur. Her constant support and help throughout this program were invaluable in organizing this event. Finally, I am very grateful to all the participants who joined us today and hope they will engage actively and contribute to the success of this course. Your enthusiasm will turn this event very meaningful. I would also like to take this moment to extend my sincere appreciation to our team of coordinators, Professor Bhupendra Ghodki, Professor Brajesh Panda, and also the student volunteers. You have worked tirelessly behind the scenes, ensuring every detail was taken care of. From managing logistics to supporting participants, your energy, enthusiasm, and teamwork has been instrumental. Lastly, I sincerely appreciate the supporting staff for their continuous assistance behind the scenes, and thank you all for your contribution. I wish you all success and all the best. Thank you.
Thank you so much, Professor Sapatti, for your kind words of gratitude. Once again, I extend my heartfelt thanks to all of you for your presence here today. We look forward to an enriching and insightful event ahead. Thank you again. And I request everyone to join us outside for a photograph, followed by high tea and networking. Thank you.
Thanks to you. Thank you.
Yes, outside.
hello, 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 hello. Hello, 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 hello. Hello, hello. Hello, 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 hello. Hello, 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 hello. Hello. Hello, hello, hello. Hello, hello. Check. Hello, 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 hello. Hello, hello. Hello, 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 hello. Hello, check, check, check. Hello, check. Hello, check, check, check. Hello. Hello, check, check. Hello, check, check.
of you know Purdue or like, you know?
Sir, put on the mic, sir.
Oh, you need mic, okay. So that's for recording or you put it here?
Recording.
So you're streaming too?
Yes, sir.
Oh, okay.
Yes, they will figure. She want to talk and it's okay.
No, sir, you can keep the mic. I'll just
No, they're streaming, so you should talk in this. You know, you don't have to. Go, you can use it. Yeah.
just 2 things. Good morning, everyone. Welcome back to this GYAN course titled Characterization of Agricultural Particulate Materials for Effective Handling and Processing. I welcome you all back to this course and I hope that you learn a lot from Professor Kinsley. And now, sir, I hand over the stage to you for the lecture further. So, this will be an introductory session.
Okay.
Thank you, sir.
Thank you. Yeah. Yeah, that's what I was asking. How many of you know Purdue? You all know Purdue University? Yeah, okay. I just wanted, that's why I was trying to connect to internet so that I can get a video pull out. I forgot to copy on my this one. But Snehida would, I know Snehida would have seen that video, but just to give an introduction, till we figure out. Okay, you all know my name, right? So I graduated with bachelor's and master's from you all know TNAU, Coimbatore, okay. So Coimbatore and then, no, I'll connect it. I just pulled it out, yeah, so that's fine. Thank you. Oh, it's connected? Oh, it's not connected, I think. It's still connecting, let's see.
Let's check the other.
Okay.
Land we require from here.
Yeah, I need the lens, sir.
Yes, you need the, you can put hotspot sometime.
What's that?
You need the video only, no? You can give the hotspot to it. You need the lens throughout or just throughout?
No, just for what? No, I can put hotspot. Yeah, thanks for reminding me.
That's fine.
Okay, so after my master's, I worked for ICAR. You all know ICAR, right? How many of you heard about CFET? CFET. I worked for close to 6 years, where Dr. Godke came from there too. Right? So then I went for my PhD at Purdue. Then after my PhD, I was a faculty at Kansas State. Any of you know Kansas State University? So I was there for 4 years and then went back to Purdue in 2015. Okay. So it's been close to 9 years at Purdue now. Okay. So you all heard about my area of work, right? So my expertise is in particle technology. Okay. Mostly anything to do with particles. Okay. Oh, okay, great, thanks. I just wanted to show you a Purdue video. That's why I was trying to connect to internet. Thanks, Dr. Godke. So when I was a PhD student at Purdue, I had lots of friends from IIT Kharagpur who did undergrad from here. They're all in, working in US, Bangalore, etc., many places.
So please connect.
Hold on, no, I will, hold on, give me 1 minute. Unfortunately, still couldn't connect to the internet, but that's okay. I'll show you the video later on. Okay. So that's okay. You would have heard about Neil Armstrong, right? So Neil Armstrong is one of the famous alumni from Purdue. Okay. What's that? Someone said something. No. You can hear me okay, right? Voice. Okay. So there are many famous Purdue alumni in India too. Anyone know any Purdue alumni in India? No? Go ahead. Pidam Chandra? Oh, okay. Yeah. Okay, he did. I know him well, yeah. Preetham, yeah. So he did PhD there, yeah. So, any of you ride TVS bikes? Okay, so TVS chairman is one, famous Purdue alumni from India. Many of you know Dr. C.N.R. Rao. Heard about Dr. C.N.R. Rao. So he was a Purdue alumni. Any of you from? Oh no, he's acting in Hindi movies too. Any of you know Dulquer Salmaan? Yes. Okay, Dulquer Salmaan is a Purdue alumni. Okay, so there are many people around. Again, Sriram Honda chairman, he's a Purdue alumni. There are many, big personalities in India who are, from Purdue. Okay. So again, I'll talk more about my research. So, I work mostly on, particles, powders, and compacts. Hopefully it works. Okay. No worries. I can do it. So this is a little old slide. So most of my work, as I said, particles as applied to ag industry, but I do work on pharmaceutical stuff too. Pharmaceutical, solids. Oh, thanks. Yeah. Pharmaceutical solids too. Any of Gatorade, energy drink. If you watch soccer, football games, you might see large Gatorade cans on the side for the players to drink. So I worked on it's manufactured by PepsiCo. Now I worked on modeling mixing of those powders. They make Gatorade from about 15 different types of powders. So mixing uniformity is a big challenge. So we developed a model for them on mixing of those Gatorade. Grain damage is one of my major area of work, modeling grain damage. So I work with, CNH and now Bayer too. When we harvest we lose about 5 to 6% of grains, during threshing, mechanical damage. So we continue to develop some DEM, discrete element, models that they use to modify their threshing, cylinder design and also threshing operation design. Okay, and in particle design, one of my recent work, I do work on slow release fertilizers. So how can we make urea release slowly without adding any chemicals? How can we structurally modify urea granules so that the release of nutrients are in a much slower fashion? Okay, and couple of my students are working on it, and then sensing dispersed dust and dust explosion prevention, mostly funded by USDA. We're trying to use imaging or video methods to get the amount of suspended dust in confined spaces. That's again one my major area of work. And I do lots of characterization, small works for pharma industries, etc. Okay. One of the recent project that we just started is 3D printing of pharmaceutical tablets. The company has a 3D printer, but we are not working on 3D printing per se, but we're working on like how to make them level. The powders, before printing, how can we make it very level so that the tablets they print are like in uniform size and shape. Okay, so those are some of my projects. So I'm as you introduced, I actively involved with the ASABE. Actually, I'm the community editor for processing now. I look for, if you are interested in reviewing papers, let me know. I can, suggest my associate editors to send you papers to review. And, I also encourage you to submit papers to ASABE. ASABE journals, the impact factors are not very high, but still it's highly recognized by the professionals in the field, right? So again, we'll be talking for 4 days, but still I want to learn from you your name, your major degree research topic, etc. Okay, I might forget now, but over the course of 4 days I will come back. Hopefully I'll remember all your names when I leave. Okay, so why don't we start from here? Except I know a couple of people, Ankur and
Hello.
Snehida from TNAU. So go ahead, Ankur. Yeah.
Good morning, everyone. Hello.
Yeah, I think it works. Yeah.
Myself, Ankur Singh. I am a M.Tech student in food processing engineering. I am working on project development of tomato sorter under the guidance of Bhupendra Godki sir.
Okay.
Thank you.
Okay. Thanks, Ankur.
My name is Particulate. I am doing M.Tech in food processing engineering. My research topic is development of assisting unit for rapid drying of defectants, drying of mango berry under the guidance of Bhupendra.
Okay. Okay. If it's difficult, you can sit and introduce too. That's fine. Yeah.
So, good morning, respected professor and all everyone present here. My name is Sanjana Vatam. Currently I'm pursuing my masters under Professor P.S. Rao, and my project topic is design of a millet grader, design and DEM simulation of a millet grader.
Okay. Okay. Great. So you started using DEM?
Yes, sir.
Okay.
I'm using Altair EDM.
Altair. Okay.
Only I motivated from your research.
Oh, sorry.
Research
No,
papers.
it's okay. Okay.
Good morning, everyone. My name is Soipatin, and I'm a first year PhD research scholar in food processing.
Okay.
And my research topic is on design of plant protein extraction equipment
Okay.
using electricity.
Which plant you're using? Which plant protein?
Till now, sir, I haven't decided, but mostly
Okay.
I'll be using high machine.
Okay. Okay.
Hello. Hello. Hello.
Good morning, sir. My name is Hina Sudhakar Tambi. I am PhD research scholar first year.
Okay.
I am under Professor Rao sir.
Okay.
My broader research area is development of process frying of food, especially vacuum frying, sir. Vacuum fry.
Take
Vacuum frying.
vacuum fry.
Yes.
Oh, okay. Okay. Good. Thanks. Yeah. And again, I said I might forget your name, but hopefully by the end of this week I will remember all your names. Okay.
Hello sir, I am Saima Nigar and I have currently joined PhD over here under Professor Praveen Kumar Sapati, and my
Okay.
broad area of research is plant protein based
Okay.
food product development.
Okay. Good.
Thank you.
Thanks.
Good morning, sir. Good morning, everyone. I'm Polumide, a first year student of M.Tech Food Process Engineering of this department.
Okay. Okay. So you haven't started any research here?
I will start from second.
Okay. Okay. Okay.
Good morning, sir. Good morning, everyone. I am Preetha Mandal, and I am a second year student of M.Tech Food Process Engineering at
Okay.
IIT Kharagpur, and my research topic is ultrasonic processing of milk and
Okay.
preparation of Indian curd or dahi from ultrasonicated milk under the guidance of Professor Anit Mandal.
Okay. Great. Yeah.
Hello sir, good morning. Myself Snehita, and I have joined your first year PhD, and I am working under Jayata Mitra ma'am. My area of research is detection of oil adulteration
Okay.
system.
Great.
Good morning, sir. My name is Mayank Dikshit, and I am enrolled in M.Tech Food Process Engineering. And my topic is I am working on developing a hybrid frying technique, and my supervisor Professor Brijesh Kumar Pandas.
Okay.
Good morning. Good morning, sir. I am Tista Mohes. I am a final year student of BSc Agriculture from Brainware University.
Which university?
BSc Agriculture.
Which university, sir?
I am a final year student.
Yeah, which university? University.
Brainware University.
Okay. Okay.
Good morning, sir. My name is Devasis Bakshi, and I am pursuing masters in
IoT in computer science and department.
Okay. Okay. Please stand up and talk. Oh, okay. Sorry, yeah, for recording purposes, okay, not for me. Okay, go ahead.
Hello sir, I am Somish. I am taken up a project on baking of bread by using hybrid baking technologies,
Okay.
that is on ohmic and infrared heating, under the guidance of PP Tripathi ma'am.
Okay. Good.
Good morning, sir. My name is Harshal Bhoite. I am second year postgraduate student at IIT Kharagpur, and I am currently working on electrostatic separation of protein, equipment for electrostatic separation of protein under Praveen Kumar Sapati, sir.
Okay. This is from cereal grains?
Yes, sir.
From cereal grains? From grains?
No, sir. It is an equipment for electrostatically separating protein, dry protein particles.
Yeah, from which products?
I have currently selected soy protein as
Okay.
a source.
Okay.
Good morning, sir. My name is Aryan Dubey. I am currently pursuing Masters in Food Process Engineering from IIT Kharagpur.
Okay, good.
Good morning, sir. I am Rishi Sachan. I am pursuing my MTech in IIT Kharagpur.
Okay.
Good morning, sir. My name is Samarendra. I'm a scientist working in ICRCISS and working on micro installation of biotic compound.
Okay. Which institute is that?
Central Institute of Subtropical Horticulture.
Oh, okay. Okay. Good.
Good morning, sir. My name is Prashant Kumar. I am second year PhD student, and I am working on sustainable protein through dry fractionation.
Okay.
And currently I am working with Professor Rao.
Okay. So if you are second year PhD, then you all should, if you are especially second year, you should try apply for Purdue, postdoctoral, doctoral fellowships, Go
Hello sir, good morning. I am Mukta, and PhD scholar here second year, under the guidance of PS Rao sir.
Okay.
Good morning, sir. Thank you for the opportunity to introduce myself to you, sir.
Sure,
Myself, Prakash. So, I am pursuing a doctorate, and I'm majorly working on seaweed processing and utilization, the major component from the seaweeds.
Okay.
Thank you, sir.
Okay, thanks.
Good morning, sir. I am Yagurendra Kumar. I did my master's in food process engineering from NIT Rourkela.
Okay.
Currently, I am working here as a project staff on GRA position under PS Rao, sir.
Okay.
Yeah, thank
Great.
you.
Yeah. So, are you a student of Preetham, Dr. Preetham?
Yes, sir.
Okay.
Good morning, sir. I am Shreyash Yashwant Shirsat. I did my master's from Institute of Chemical Technology, Mumbai.
Okay.
I worked on non-thermal technology, cold plasma.
Okay.
So I explored the effect of cold plasma on maltodextrin, and currently I am working as a junior research fellow under PS Rao, sir.
Okay.
Thank you, sir.
You introduced right already, yeah.
Yeah, we already met,
Yeah,
so I'll introduce myself. I'm Dr. Ronit Mandal. My area of specialization is food process engineering. I'm assistant professor.
Okay. Great.
Good morning, sir. I am Kushal Thombre. I am pursuing MTech in Food Process Engineering from IIT Kharagpur. I am working on rapid detection of tea quality under Dr. Abir Chakravarti.
Okay.
Thank you, sir.
Good morning, sir. Myself Anup Kumar Sardar, and currently I am doing MTech in Food Process Engineering second year, and my area of research is 3D printing of foods and vegetables for personalized nutrition.
Okay.
And under the guidance of Punadasan Punam Tripathi ma'am.
Okay.
Thank you, sir.
Great.
So, good morning, sir, and fellow participant. My name is Mandar Moe. Currently, I am pursuing Masters in Food Process Engineering, second year MTech student. So, I am working on the study of different pretreatments and quality kinetics of millet-based vacuum fried snack under the guidance of Professor Srinivasa Rao.
Okay, great. So,
good morning, sir, and everyone presented here.
My name is Aniket Masne, and currently I am pursuing a Masters of Technology in Food Process Engineering.
Okay.
And my research topic is development of colorimetric indicator for milk spoilage using nanoparticles under the guidance of Professor Kanik Bunia, sir.
Okay, great.
Thank you.
Good morning, sir. My name is Rajshekhar Hasda. I am an undergraduate student of BSc Agriculture in Vishwabharati University.
Oh, okay. Do you, by any chance, do you know Dr. Gautam Mandal?
Yes, sir.
Okay, you know him, okay. He was my past colleague at ICR, okay. Yeah.
Good morning, sir. I'm Chayan Mandal. I'm also UG student in Vishwabharati University.
Okay, okay.
Good morning, sir. I am Akashnil Koibarto, and I am undergraduate student of Agricultural Science at Vishwabharati University.
Oh, okay. Great.
Thank you, sir.
Good morning, sir. Myself Hilal De. I am the second year MTech student from IIT Kharagpur. My research topic is to development the low glycemic index rice.
Okay.
Thank you. Under the guidance of Dr. Jayata Mitra.
Okay.
Good morning, sir. Myself Mukesh Kumar. I am PhD second year student. My research topic is design and performance evaluation of dual stage low temperature spice grinding machine.
Oh, okay.
Under the guidance of Dr. S. Thangalakshmi.
Okay.
Thank you.
So I don't know, maybe Dr. There was lots of work on cryogenic
Yes,
grinding long time ago. So you're using cryogenic process too?
Yes, sir. I am currently PhD from NIFT Sonipat.
Oh, okay. Okay. No, then, yeah.
Good morning, sir. I am Sitesh Kumar. I have recently completed my PhD degree in Food Process Engineering at IIT Kharagpur, and my research topic was effect of cold plasma processing on quality and self-extension of kiwi fruit juice, working under the guidance of Professor P.P. Srivastav, sir.
Okay.
Thank you, sir.
Great.
Good morning, sir. My name is Anindya Krishna Basu. I am first year MTech student from Tezpur University.
Okay.
And I haven't started any project yet, but my research interest is on the nanotechnology in food applications and extraction of bioactive compounds.
Okay.
That's
Great. Yeah.
Thank you, sir.
No problem. Yeah.
Good morning, sir. Myself Anand Kumar. I am MTech student. My project topic is microencapsulation of okra mucilage, characterization and process optimization under the guidance of Professor Bhupendra Mangurki.
Okay, good.
Good morning, sir. Myself Nishant Ghormare. I am currently pursuing Masters in Food Process Engineering at IIT Kharagpur. I am working on development of test method for degree of milling of rice under the guidance of Professor Brajesh Panda.
Okay.
Good morning, sir. My name is Yoshim Kaping. I am currently in my second year MTech. I am working on safety of quality of asafoetida under the guidance of Brajesh Kumar Bantas.
Okay, sure. Thank you. No problem. Hey, thank you all. So thank you all for introducing yourself, and thank you all for being here. Okay. So how many of you are excited to learn about characterization? Okay. At least for the sake of, for now, raise your hands, okay, right? So that I can see all your raised hands, right? So when it comes to characterization, when we talk about characterization, what comes to your mind? So what do you mean by characterization? Okay, classification, or someone said some other response somewhere. Okay, physico-chemical properties, what else? Okay, particle behavior, yes, particle size. So there are tons of things comes to our mind, right? So, characterization means like, trying to put them in a group or class, right? So that we can use that group for further information, right? So how do we use, when to use, any kind of powder or material will depend on what type of characteristics that has, right? Like physical properties, chemical properties, etc., right? So why do we use this characterized material, or what is the purpose of this? Designing equipment. So can you give an example? This is your quiz. Yeah, quiz is on Friday. Okay, till then no answers are wrong in the class. Okay, so you can give wrong answers in the class too. Okay, but not on the quiz. I believe the quiz is on Friday. Okay, so again, so we use characteristics for pneumatic conveying, design of pneumatic systems, right? So what property we use for pneumatic system design?
Surface properties of operation it will cost to the
Surface properties maybe, but there is major what's that? Terminal velocity. What is the property that determines terminal velocity? Specific gravity. Yeah, specific gravity means, what is specific gravity? Density. Okay. Yeah, so it's a density, right? So density is one of the major property that we use to characterize pneumatic systems, right? So that's a major property. Then particle orientation, that will affect the drag, all other things will come into play, okay? But the major property will be, we start with the density, right? Any other examples where we use property to design or anything?
Angle of repose design for
Yeah, we'll talk about that. We use for angle of repose as hopper angle, but that's the wrong approach. We'll talk about that. Okay. So, any other, example? What's that? Okay, coefficient of restitution. Okay, yeah, I know you are working on DEM. Okay, I'll come back to that in a minute. So, someone else said, what is that? Someone responded. Yeah, particle. So where we use application. What's that?
binding properties.
Yeah, but I'm coming into property. Okay, so, but what is the application? Where do you apply? Okay, new food. How?
In pharmaceuticals for developing tablets.
Okay, good.
Particle size is used for design of the screening.
Screens, yeah, screen size. Okay. So, size separation, right? So, particle size, one of the major and basic, characterization that we'll have to do, right? And again, we'll talk more about that. Coefficient of restitution, again, yeah, maybe, okay. But how do we measure coefficient of restitution? Okay. Yeah, if I say that's wrong. Okay. So basically it comes, we'll talk about coefficient of restitution later part of the class. Basically, how much energy we lose during impact. Okay. But again, I have used velocity before and after, but that's a wrong approach, But there are not many good approaches to measure coefficient of restitution. It's still evolving. Okay. So the major challenge here is, if you take about characterization, if you take, if you take any agricultural materials, right? We get tons of different types of agricultural materials, right? It could be food, like for example, Skittles or M&Ms. We call as M&Ms. Tablets, compacts, soil. That's corn cobs. That's piled in large piles, corn, fertilizers, etc. They all come in different sizes and shapes, right? So how do we characterize them uniformly? Or all these sizes and shapes makes it very difficult or very, very challenging to characterize or measure their properties of, okay? And hopefully we'll, go through some of those characterization in this class. This is almost a condensed version of, what I teach at Purdue. It's in, combined class for mechanical engineering and ag engineering students, but, chemical engineering and aeronautical students to take this class. So it's a condensed version of what I teach at Purdue, okay? So, but I'll not be able to cover everything in 4 days, but I'll try to cover more, okay? So goal, we'll go through some of the characterization approach, hopefully most of them, in this 4 days, describing different properties that, used to measure sizes, shapes of particles, powders and compacts. Again, I'll go through some of these fundamentals behind measurement of these properties and how these properties influence, downstream processing, equipment design, etc., etc. Okay, I'll go through some of those examples. Okay. Again, how many of you have calculators? You all? Okay. If you don't have, if you try to bring a calculator, okay, we'll have some in-class examples, okay, that you will be solving, okay. So what do we care about property? Again, most of the time, especially when it comes to food industry, it's for quality, right? So for quality purpose, we need to know their properties, right? It could be physical, mechanical, etc. Okay, and okay, I'll just give another example. You all eat wheat flour, right? Chapati, roti, right? We use wheat flour, right? Do you know the size of that particles? Wheat flour particles. Food engineer, you are eating wheat, right? Rotis. What's it?
Less than 250 micrometers.
That's an excellent guess. Okay, but still not very close. But it's very, very close. Okay. Anyone else? So the average should be close to 140 microns, at least for the US standards. Okay, 140 microns is the we call this Code of Federal Regulations in the US. Okay. So how do they check for the size? In general, they any of you been to a wheat flour industry, wheat milling industry? No one. Okay. So if you go to visit any wheat mill, there will be continuous rollers or milling machines. Okay. So when from all the rollers they collect flour and then they check the particle sizes. Particle size matches, then they say okay, it can go into that flour category. Okay. That's the simple basic check they do, but the most common check that they do is for ash percentage of ash in wheat flour. Okay. Do you know how ash affects wheat flour? Percent ash, or mostly how much fiber it goes in there. Any guess why ash is important? Minerals. Maybe, when you mill into wheat flour, we don't get lots of minerals, very limited. So, anything else? Any guess?
Outer layer mostly contains the outer layer.
Not really. No, it affects the processing characteristics, processing behavior. Any guess? 1 more minute, quickly. What's? Any guess? Okay, it affects the baking properties, okay, how puffy it becomes, okay. So, different ashes, if the percentage is ash is high, if the percentage ash is high, their baking property will be very poor, right, especially if you wanted to use it for cakes and things, cake flour, we want your, ash to be very low, but for wheat and roti, it can be a little high, but in general, they keep it as about 0.5%, okay. So, again, property again for prediction of behavior, right? When it comes to bulk, most often we don't measure their behavior, but we try to predict their behavior, right? How material behaves when it flows from a large hopper, large bin, and when we mix bulk volume of powder, we try to predict by using those properties, right? Most common you would have seen empirical correlations, right? Statistical correlations, statistical relationships, relating powder property or particle property to their final performance, right? Most often it doesn't correlate very well. We try to do some first principles modeling, like using their understanding, using their fundamental property, understanding the physics, like what mostly we do in DEM modeling. Okay, try to understand the physics, and then use that physics to apply and understand their bulk behavior. Okay. For those, property measurements are very important, and again selection of sub-samples for testing, right? I just talked about wheat flour, wheat milling, right? You cannot test the property of wheat flour all the time, right? 24/7. So we just go and grab maybe a ½ kilogram sample or 100-gram sample, like maybe once in 2 hours, okay? but that 100 gram sample should be representative of like tons and tons of materials you are producing daily, right? So 100 gram of sample should equate to the tons of material. So how do we, subsample or take surrogate materials for, characterization, etc. Okay, and again we'll go through some of these measuring properties is very important. Okay, we talked about angle of repose, right? So that's why we always say angle of repose is not a good property, but it's an easy property to measure. Okay, just as an example, if you see this pink color powder, how many angles you can measure? So if you take that pile of that powder, you can at least have like 3 or 4 angles of repose. So which one will be its actual property? We do not know, right? So it might not be, you can measure an angle here, you can measure an angle here, you can measure an angle here. So if you use either one of those values, for design purposes, the other 2 angles may not match, and then your design might be poor or wrong, right? So again, so that's why we say measuring properties is very important. Again, very commonly used for angle of repose, very commonly used for indicating the powder flow, hopper design, etc. But in general, it doesn't match with the actual bulk behavior. Okay. And we'll talk about angle of repose later on. Again, I'll skip through this. Okay, so there are tons of characterization approaches we use, right? So one common characterization approach is simulating the process experimentally, okay, or experimental measurement. So we do use different characterization equipments, right? We try to simulate the process and then measure the property of interest. Okay, so again, a couple of examples. If you wanted to see the bin outlet or opening of bin, how much minimum opening is needed for the material to flow, we try to use. I'm not sure how many of you seen an equipment called Flodex. Flodex, no. It's a small, it's not an expensive equipment. Small bin-like instrument. It will have a hopper opening with different orifice, openings. So you use different openings and see at which opening the powder will flow. Okay. So again, we can use that to simulate the actual process and measure. And also another example, attrition of tablets is not only in pharma industry but in food industry too. When you make compacts, the attrition is a big process, right? We lose materials or we lose products, right? So we try to simulate the process of handling by putting the tablets in a rotating drum and mixing for a period of time, and then from the amount of samples lost during this process, then you calculate the amount of attrition, right? Just to simulate the handling process, okay? Or we can use some measure fundamental properties and then use some models. It could be mathematical models or statistical models, and then define their properties. Okay. So this will be a little easier, right? So the fundamental property or fundamental value of the material, and then use some correlations. It could be, most often we use a lot of times we use statistical correlations to again extrapolate those properties, right? Very commonly you would have seen bulk density of different materials, right? So how moisture influence bulk density, you will see a statistical equation or relationship, right? So again, but there are other physics based models too. We will go through some of those, at least for powder flow. Okay, I might not cover for tablet attrition or wear models, but there are physics based models too, okay, that we can apply. But both experimental approach and physics based or theoretical based, both have their own advantages and disadvantages. But modeling, again, it comes from the physics based fundamental measurement, right? So that gives much more reasonable estimation of the property than an experimentally measured property most often. Okay, but again, the challenge is we do not know when the system changes. We still don't have the understanding of how the properties will change. Okay, just one quick example. You might have seen large handling of powders, right, or grains, etc. Right. So if you are conveying in a auger conveyor, their properties will be little different than when you use how many of you seen drag conveyors, drag systems? No. It's called paddle conveyors too. So their properties will be okay. I will not go into those. Again, their properties, the importance of properties when we change handling system will also be different. Okay. But again, we should be able to predict the bulk behavior, but again, we do not have much understanding from, when we move from one scale to other scale. Okay. We talked about 100 gram of powder, right? So 100 gram of powder will have completely different property than if you are talking about a ton of powders. Okay, 1 ton of powder. So we still do not have much understanding on when moving from one scale to another scale. Okay, small scale to a larger scale. Okay, so again, very important to make measurement at different scales, and which is challenging too. Okay. So in this course of 4 days, hopefully I will go through sampling, some size measurements, and up to powder constitutive loss. Okay. So that's the syllabus for this 4 days. Okay. I will be learning in this class. So any questions? Again, if you have any questions anytime, feel free to stop me. Okay, just raise your hand. Okay, I will be happy to discuss or talk. Okay. Any questions? How many of you need tea? I'm just asking how many of you are still awake? You all are awake? Okay, it's good. So let's go to the next. Or do you need a break? No? Okay. Okay, so the first basic thing, when it comes to particles and powders is sampling, right? Subsampling, right? So whenever you characterize or measure some properties, we take small amount of sample, right? Is that right? Yes or no? Okay. I need response. Okay, if not, I will also feel sleepy. Okay. Okay, we'll talk about sampling of powders. Okay. So again, the goal of sampling, and as I said, give an example of wheat milling, right? We'll be milling tons of wheat, but when it comes to measuring the ash percentage or measuring the particle size of wheat flour, we just take like 10 grams or 100 grams, right? So how do we take that 10 gram or 100 gram from that tens of tons of material, right? So that 10 grams or 100 grams, whatever you subsample, should be representative of all the tons of materials you are producing, right? So that's the purpose of sampling. And then again, how do we sample, depend or define your product characteristic too, okay? So how many of you do sampling in your lab when you characterize? Do you sample, right? So how do you sample? Give some examples. Come on. How do you so?
We just mix it up properly and then we.
Okay. How do you mix?
Mostly I work with 1 and 2 kg of samples, so we can mix it with hand.
Okay. What sample you?
Rice.
Rice. Okay. Anything else? Any other method that you use? No? No understand. Why you all are quiet? Still thinking? Okay. So just give me an example. Okay. So for example, okay. So you would have seen lots of large samples come in large bags, right? So I'm giving an example here, like 250 kilogram of tote bags. Okay, powders coming in 250 kilogram tote bags, but you want 2 grams of particles or powder to measure the particle size using laser diffraction. Okay, so how will you subsample 2 grams from this 500 kilogram? Mixing will be a little difficult, right? Okay. Okay, yeah, that's what 1 gram. You can take 1 gram for each. Okay, but how will you take that 1 gram?
Maybe at different positions.
Okay, different positions. Okay, that's good answer. Okay. Any other thoughts? Okay, shaking. How do you shake? Do you need a very large shaker for this, right? Manual? Yeah, spatula, yeah, that's the common sampling procedure that we use, right? Just use a spatula or spoon, just take 1 gram, right? Okay, so we'll talk about that methods, okay, what disadvantage, advantage, of these methods have, okay? And we'll talk about different sampling methods, okay? So when you go to any process industry, in general, we see different types of sampling, okay, outline, inline, online, offline sampling, etc. Okay, so online usually you don't remove the sample. Okay, so for example, again I'm going back to wheat flour, wheat milling process. The flour will be still in the pneumatic handling system, but there could be a laser diffraction or laser system that measures the size of those particles on the floor. Okay, so those are online is very common nowadays. You would have seen many industries using NIR, near infrared systems, so that you don't have to take the samples out. On the floor you measure the characteristic. Okay, outline is very common. That gives more. That helps with a little bit more advanced understanding of the particles. Okay, so again, online systems in general we cannot characterize them using their direct property. Most often we use their indirect properties like near infrared, optical property. Those are very common. So those are like not direct properties. So but outline, we will be able to characterize them using their fundamental behavior and fundamental properties. Okay. Offline, most common, when you wanted to do a thorough investigation of their characteristics. Okay, you take the sample, okay, store it in the lab. And then again, most often you keep the samples for longer duration, like 3 years, 5 years, etc., till you need, the samples. Okay, you would have, know about grain grading, grain trading, etc., right? So in general, the grain graders, who check the quality of rice and wheat, etc., they keep the sample for like 3 to 5 years. Okay, they measure the quality, but they are supposed to keep the samples for longer time, since if there is any trade dispute or anything, questions comes up, they want, they will go back and measure the property again. Okay, so those are helpful in offline measurement. Okay, there are not I will not be reading all the verbatim here, but there are more advantages, disadvantages, depending on your process needs. You choose outline, online, or offline systems. Okay. Again, online you use mostly indirect properties to measure, but very quick and easy method of measuring those values. Offline, as I said, it gives very detailed measurement of the properties. Okay. Again, I'm not going to read all these things. There are tons of advantages, disadvantages here. Okay. So again, sampling bias. Okay. So sampling bias is major challenge when we subsample powders. Okay, so when you are taking 1 gram, you said you're mixing mixing rice and picking subsample, right? Rice is a free flowing material, so if you mix, they segregate. So that then again that leads to some challenges in subsampling. So you will be sampling a segregated mix. But if you are using a spatula, then again you are sampling an already segregated sample. Okay. So if you are taking from the top, it's already segregated. So you are not getting the property of the exact powder, exact mix of the powder. Okay. So again, as your sample said, you're collecting, samples from a different height. Then most commonly, if you wanted to collect, samples at different height from a large tote bag, we use a probe called thief probe. You would have seen or you would have used thief probe. Again, that can, destroy the sample when you, insert those thief probes into those bulk bags. That will also introduce bias, in the measurements. Okay. So again, very challenging process, sampling. Sampling. So again, we'll have to take extra care so that we are introducing any bias during, sampling that affect your property measurement or property characteristics. Okay. So again, general, total measured variance. How much variability in the sample, we'll come back to that, towards the later part of the lecture too. So what we are interested is actually characterizing or quantifying the actual variance in the sample, right? How much the property is different. But, unfortunately, we introduce lots of, variance from the sampling, right? If it's already segregated, then you are introducing a bias. And also from the analysis, if your instrument is not calibrated well, if your instrument itself has some error in measurement, then you are adding another variance. So there will be 3 different variants, that we are introducing into subsample, measurements or characterization. Okay. So it's the easiest to control here, which is the easiest bias that we can avoid. Analysis, it's highly dependent, it's not your, issue, right? It's an instrument problem.
You can calibrate the errors.
Most often, but still, you may not know, right? So most often, the maximum variance that you can avoid is the sampling variance, right? If you use appropriate sampling, then you can avoid that variance, okay? So sampling, that's the easiest to avoid. But variance due to analysis also, again, if it's calibrated well, you can avoid, but most often, you will still end up with some instrumental error. Okay. Again, one of the, important thing that you have to keep in mind is, you can have an advanced measurement technique, okay, but your sampling is very poor, okay, then you are not characterizing the actual property, right? So you can have like $1 million equipment for measuring particle size, but if your sampling is very poor, then you are wasting your $1 million to measure the particle size. Okay. Okay, so in general, we follow 2 rules. Okay, when you are sampling. So one is, again, the powder should be in motion when sampled. I thought I had an example before going into this, but I don't see. Okay, I have it in the next part. Okay. So when you subsample powders, you have to keep in mind 2 rules that you have to keep in mind. One is the powder should be in motion when sampled. Okay, it should be flowing, and the other is many samples should be collected in frequent interval rather than just one sample at one time. Okay. Again, I will go back to the flour milling, wheat milling example. Okay, so if you are collecting, for example, wheat, before it's milled, what we generally do is, when wheat kernels are unloaded from the truck, you subsample when it's flowing from the truck. Okay, you take subsamples and then analyze them. Okay, same thing if you wanted to measure the particle size of wheat flour. Okay. So then you go and collect, different samples at different intervals, and then measure their particle characteristics, baking characteristics, etc., etc. Okay. So at least any granular material, any particulate material, okay, if it's a solid, you should keep in mind these 2 rules. Okay. So why we have to sample them when it's in motion? Why, why it's better to, take subsamples when it's flowing? Okay. Okay. What type of uniformity? Very close answer, yeah. What type of uniformity you mean? Oh, what is that? Maybe, not usually, not always. Bulk density can differ too, depending on fluidization conditions. So how much air is there? Okay. Okay. Yeah. Size distribution. Yes.
Particle size also.
Okay. So mainly, if it's flowing, then the chances of segregation will be low. Okay. So when it's when it's stagnant, okay, so the powder itself would have already segregated, right? So when you subsample from a stagnant powder, then you are subsampling from a segregated bulk. Okay. So when it's flowing, you are avoiding subsampling of segregated bulk powders. So that's why we mainly say sample when it's flowing. Same thing, lots of subsample, so that we are characterizing or collecting powders at different intervals. So if there is some process change downstream, okay. Just again going back to wheat milling example. If you have 6 roller mills, and one of the roller mill, the mill is not very good, okay, so that might not produce a good quality flour, okay. So that will come at specific interval, that flour will come at specific interval and mix with the general all the string, powder string, okay. So if you are taking just one sample, you may not identify the issue in the mill, since you are not gathering sample at that time. So if you are collecting lots of samples at different times, then you might be able to capture the issue with the process itself too, okay. Okay, again I ask lots of questions, okay, in the class. That's my style, okay. Make sure again, as I said, there is no wrong answers in the class, okay, except for Friday, okay. So again, that's the objective is to make sure the subsample that we are collecting is representative of the bulk of material that we are producing or shipping or handling, okay. Any questions so far? No questions? Yeah, go ahead. Yeah, go ahead. I will come back. Yeah, go ahead. Okay, the large bags. Okay, we'll talk about that in a minute. Okay, go ahead.
Should locations also vary with in the stream?
Yeah, locations will also vary. Yes, yeah. So we'll have to, depending on the objective of your process, we'll have to find a location appropriate, a location within the process that gives your objective. Okay. Any other questions? No? Okay, so we'll move on to the next part. So we'll talk about some sampling methods and equipment, okay. So one example here, okay. So a powder is transported by a conveyor belt, and the powder, it's discharges into a drum. Can you describe an appropriate sampling procedure? How do we sample powder when it's flowing? And again, it satisfies the first rule, right? The powder is flowing, you are sampling when it's flowing, okay. So can you develop an appropriate subsampling procedure for this system? How do we sample the powders?
So as it is flowing, it is maintaining the
Okay.
first rule, and for the second rule, we can take from different positions.
Okay.
1 gram or
Okay.
something,
Okay.
Material, and then we can do the sample.
Okay. Okay. So very good. So you'll have to, one condition is applied, satisfied, right? You are sampling from the flowing stream, right? then how do we, one minor change in that answer will be okay. So you cannot collect from different locations, okay. So it's flowing from the powder, okay. So if you are collecting from different locations, what happens is you are, when it's flowing, there could be some differentiation due to changes in density, okay, or particle size, okay. Sometimes the larger particles will flow differently than smaller particles, right. So if you are picking, from random locations, you might get a segregated mix still, okay. So what we have to do is use a large container, okay, and then run it through the flow stream, okay. But again, this is a bad subsampling procedure. So you cannot run the container to and fro, back and forth through the flowing stream, okay. So only one motion, okay. So this is wrong, but either take the container through the stream from front to back, so you are getting all the segregated mixtures too, okay. If not, from side to side, okay, one side to the other side, okay. So again, you are gathering all the segregation or possible segregation within the stream when it's flowing into the container, okay. But again, if you are running it back and forth, then you are collecting a segregated mixture, okay. So there could be some segregation of the powder within that subsample, okay. And again, sample stream at multiple random times. One of the important thing that you will have to keep in mind is if you are using a container, the container opening should be greater than equal to 20 times the particle diameter, okay, so that you are not losing any larger particles, all the particles are falling inside, okay. Again, you don't want the container to be full when you are sampling, and again, why means you don't want any overflow from the container, okay. So make it's full till 3/4 of it, and then use it for subsampling, okay. Any questions? Okay, we're getting lots of examples from food, right? But agriculture, your students in agriculture, right? So, you should also give some examples, okay, when I ask questions, okay. So you joined late, so can you introduce yourself to the class?
Sir, I'm Debati Tamaji, and I'm doing MTech, second year in food process engineering.
Okay. Okay, so what's your research on?
My research is on hydrocolloids effect.
Okay.
On pea protein based meat analog.
Okay.
Extrusion technology.
Okay, great, yeah. Okay, so another option is you stop the belt itself, okay. So if you stop the belt and then use some cutter sample, there are you can get these in markets, sample cutters, use some sample cutters or sample dividers and gather samples from multiple portions within the belt, okay. Though it's not satisfying the first rule of sampling, it's not flowing, but still you get different mixes of powders from different locations, okay. So that will be again a good approach. There are again tons of different subsampling systems. In any of you been to a bulk production facility? No, mostly particulate material like fertilizers, soil, mines, mixing. So you might see one or other type of subsampling systems in those bulk production facilities. Common one, collection chutes, these are very common. Sampling, these kind of containers back and forth that pulls subsamples, and those are very commonly used subsampling systems in bulk material production facilities, okay. And there are tons of systems, many methods available, okay. So as I said again, it's a large, if you are sampling from a large container, you should avoid because it's mostly already segregated. So what you are collecting is already a segregated mix of powder. So the option that we usually, what pharmaceutical industry at least does is, if they wanted to subsample from a tote bag, like a 250 kilogram bag, they pour it into another container, okay, and again, so you are satisfying the first condition, the material is flowing, right? When it's poured, then they subsample from multiple locations when the material is flowing from the tote bag into another container, okay. So if you cannot do that, then use some thief sampler or other subsamplers and collect samples at different locations within the within that tote bag, okay. So that's one, if you cannot avoid. But again, we always use scoops, ladles and stuff, right? We'll talk about that in a minute, okay. So why sampling again is a problem? Again, segregation, you would have seen this picture a lot, in internet, right? So bulk powders, they segregate a lot, right? So it can segregate based on the difference in composition, difference in density, difference in size. Lots of properties influence their segregation. So if you are taking sample from the surface, for example, if you're picking like scooping from the surface, you are not gathering the powder from inside. So you are getting a segregated bulk, okay. So that's, again, that should be avoided. Same thing for when you are transporting bulk material in trucks and containers. Usually, so which material? Okay, I have the color there. Lighter material comes to the top, right? Do you guys know the name of that effect? The name of that effect. Why smaller, lighter materials come to the top when you're. Okay, so do you know the name of the effect? Buoyancy, yeah, but there's a particle name, for particle segregation. Okay, you might have not heard. So it's called the Brazilian nut effect. Okay, so you might, if you just Google YouTube, there are tons of videos, Brazilian nut effect. So larger particles, or lighter particles, segregating. So in general, larger particles come to the top, and lighter materials, again, come to the top. Okay. You all would have seen, nut bags, right? Nut mix that comes in small plastic bags, right? Nuts, peanuts, other types of cashews, etc., mixed in a bag, comes in small bags. Usually, when you see those bags, the larger nuts, for example, cashews, will be in the top. The smaller nuts will be in the on the bottom, right? So that's again, differences in size that leads to this segregation, okay? But again, going back to the nut bag example, okay, how do you avoid, segregation of those nuts within a bag? They do add some other materials inside the nut bag so that they don't segregate. Any guess, any thoughts? What material they add to avoid segregation in nut bags? No? Any quick guess? No? So, most of the nut bags will come with raisins nowadays, right? Raisins, dried grapes. So raisins are cohesive, so they avoid segregation. So they keep the materials in place, okay? That's again, they add it as healthy too. But, so going back, we'll talk about those segregation, Brazilian nut effect later on, okay? So again, if it's based on density, based on sizes, the materials segregate. And if you, scoop or, take small amount of sample, what you get is a biased mixture. So that's why we avoid, we try to, avoid static sampling and also using scoops and ladles, okay? But scoops, very easy, right? You just go and scoop, right? But, if it's not, avoidable, then again, we can still use, many people, we still use in industry, okay? But couple of things to keep in mind, again, don't allow these samples to overflow when you're scooping. So when it's overflowing, what happens? The larger particles will roll off, okay? So you might not get an accurate, again, accurate mix of the samples from the bulk, okay? But it's, scoop can be used if the particles are cohesive or the material is cohesive. Cohesive materials don't segregate, right? So if they don't segregate, then you can use scoop, you don't have to worry about segregation. But if it's free flowing materials like grains, free flowing powders, larger size materials, then scoop is not a better or ideal method for sampling, okay, because they segregate a lot, they lots of other factors that leads to segregation, okay. Thief probe, again, it's very common. If you cannot make them flow, if you cannot take subsample from other means, you can use a thief probe. Thief probe means long probes, either with multiple pockets inside or one simple. Again, usually the probes will have pockets depending on the type of powder and orientation where you want to sample, okay. So you collect samples from the ideal location or from multiple locations and then mix them together and then subsample, okay. It's very common in large storage structures if you cannot subsample. For example, if you are large grain storage structures, grain bins, large structures where we store fertilizers, etc., you cannot use any other subsampling, okay. So you'll have to use these kind of thief probes or pocket probes, etc., okay. Again, very easy to use, simple to use, but again gives a decent amount of subsamples from the bulk, okay. So far, at least it's if it's if it has some periodic segregation issues, then one of the research said for at least for pharmaceutical powders, if you use an N sampler, that gives a better result than these kind of samplers with multiple pockets, okay, or one subsampling at the end might give a better result of subsampling than other devices, okay. I'll skip this one, okay. So sampling from trucks and rail cars, in general, this from again Canadian Grain Commission, they suggest to sample from at least 8 locations within the rail car or within the truck, okay. So if it's manual sampling, it will be a little challenging, but most of the grain handling processing facilities nowadays have the automated pneumatic samplers. I will show you a picture in the next slide, okay, that goes till the bottom of the truck, okay. So what happens is, again, before these pneumatic sampling systems, okay, so manual sampling we cannot sample till the bottom of the truck, right. So what people do is they put the poor quality stuff at the bottom and fill it with good quality on the top. So when they subsample, you get the good quality material on the top for getting better price. So but now they cannot avoid, since with pneumatic systems they can go till the bottom of the truck, okay. Again, pneumatic, very similar to the thief probe, but it operates based on using pneumatic like suction principle. So the probe goes to the till the bottom of the truck and then sucks samples at different heights, okay, and then gets the quality. Very, very simple and easy to operate, okay. There are other sampling equipments too, little high end, we may not use in food and grain processing industry, but there are X-ray, gamma ray, NIR, NMR systems that can, these are mostly used for, inline and outline, measurements, okay. So use them and then, take subsample, you don't take subsample, but, measure, the sample at, in the process itself and then characterize them. Freezing a sample is another option. Again, these are mostly used for high value products. If it's very expensive, most common in pharmaceutical process. Even in pharmaceutical industry, 1 gram itself is very high value, right? So they use these kind of high end subsampling procedures. Freezing, again, adding liquid binder, then freeze them, that portion, and cut them, so that you save the integrity of the sample till you analyze. You are not adding any additional segregation, adding any other, you are not breaking the sample, etc., while handling and taking to the measurement unit. Okay, any questions? Go ahead, yeah.
For the chalk and breakers, you said that the pneumatic system will be used for this. What will be the state of the car or the truck where the grain is being stored?
Oh, it'll be idle.
It will be on steady state.
Yeah, in steady state. So what happens is in, at least in the industry, so near the gate when the truck comes in or even rail car comes in, they stop at the gate, then they pull sample. The truck will be idle, they pull samples at multiple locations. Then, they measure the quality. Based on the quality, they choose where to send the truck. What's that?
If a truck means the tons of material, they will reject the whole truck.
Yeah, they will reject the whole truck. Or, they reduce the price. They could reject, they could reduce the price. If the industry wants more sample, they can do additional processing. For example, if it's high moisture, then they send it to the dryer to dry it down before storing. So they choose based on the quality, like starting from price and where to send the material. Okay.
And there is one thing,
Yeah.
for the freezing one, the freezing is done before sampling?
Yeah, before sampling. So
Just to restore the shelf life of the product?
no, not for shelf life. So when, for example, if the material is coming in, a belt conveyor system, okay, if you are subsampling, still there will be some segregation, there will be some particle breakage, etc., right? If you don't want that to happen, you stop the belt, add some liquid binder, for the material that you wanted to sample, and freeze them, and then cut them and remove. So you preserve the integrity of the sample as such.
Okay. And during the sampling, that will be in freeze state?
Yeah.
Okay.
And then you take it out, then you analyze the characteristics.
Okay, sir. Thank you.
Okay. Problem. Good questions. Any other questions? Go ahead.
There is the probe where 10 degrees Celsius is shown. What is the significance of that inclination angle? That 10 degree?
So usually that's easy to go and say. That's a good question. So just for penetrating that, tube to inside the grain mix. Okay. So if you are vertical, again, mostly if you have lots of, impurities, then vertical immersion of this probe will be very challenging. So it goes little slanting. And this is for one system, 10 degrees. It's not always fixed.
Okay.
Yeah. And depend on the type of grain, type of material, etc. Okay. Good. Any other questions? Okay. We'll move on to the next one. Okay. So sampling schemes, sample size reduction. So again, we will talk about that. I believe we will do some, again, if calculator, will do some calculations too. Okay. So there are three different types of sampling schemes the industry use. Okay. One is kind of pure random sampling. Okay. So I'm giving example of belt here, but it's common for any type of process. Okay. So random sampling, if the material is flowing in a belt, you just pick it, just go randomly. I go at 10 o'clock and then I sample powder. Then again I go back at 2 p.m. and then collect some sample. Then I might go again at 2:30 and then collect some. So it's completely random. Okay. But again, some sampling, some industry use systematic sampling. Okay. At every hour, every top of the hour, I go and subsample. Okay. So 12 noon, 1 p.m., 2 p.m., I go and subsample. That's again systematic sampling. The third, little bit better approach might be, again depending on the process, is stratified random sampling. Okay, you fix the period. Like if you wanted sample once every 2 hours. Okay, you fix the time period like 2 hours. Once every 2 hour time window, I need a sample collected. Okay, but within that 2 hour window, you don't fix a time. You go at any time within that 2 hour window. Okay. So it's randomized within that 2 hour, but every 2 hour you go and collect a sample. Okay. So these three are very common. Again, random, completely random. Again, systematic. So you fix the time, and then random stratified. So random and random stratified are very common, but systematic, it's not very common, because it might not capture, sometimes it might not capture the process changes that are occurring within the process stream. Okay, that might not be very accurate, but most common is random stratified, but random is also. Okay, and again handling bias. So you take sample, right? So you will have to analyze them, right? So you take sample, you have to transport them to your lab or to any facility, right? So during handling, there could be some bias, like it could segregate, right? So as you said, you are producing tons of wheat flour, you are collecting 1 kilogram and then bringing to your lab here. Okay, so while handling, there could be some segregation of material, right? So within that 1 kilogram, or particle breaking, change in condition. For example, you're collecting. Is it usually humid here in this place? So high humid, but if you're collecting some sample from low humid regions and then bringing it here, so the humidity, temperature will also change their properties, right? So you are introducing some additional bias during those handling process. Okay, then again, one of that not always common, not always possible, but what we suggest, at least for industry, is you have the process similar. If your production process is in a high humid condition, then you do the characterization in also in a high humid condition. Okay, because if you are measuring at low humid conditions, it might not exactly replicate the particle data that you will see at high humid process conditions. Okay, but that's again not always common, but it's always suggested if you are working in an industry. Okay, so scale, at what's the scale of sampling or subsampling or scrutiny that is needed. Okay, so when you for example, when you increase the scale, your uniformity goes up, right? But when you reduce the scale, your uniformity might go down, right? So the scale will again depend on your process. For example, again, just an example, if you take this black dots and white squares, if you take a larger scale, then it almost gives a uniform mixed indication, right? But when you take a smaller scale, okay, so there is no mixing at all, right? So the scale will depend on the process and the product that you are manufacturing. Okay, I've given a couple of examples here, right? If you're making a compact or pharmaceutical tablet, your scale should also be same as the size of a pharmaceutical tablet. Okay, or if you're making a roti, okay, from wheat flour that we have been talking about. Okay, so your scale should match the amount of flour that is needed to make a roti. Okay, like 50 grams means, I don't know how much we need for a roti, but I'm just throwing out a number. Right, if 50 gram powdered wheat flour is needed to make a roti, then your scale of scrutiny should be 50 grams. Okay, so taking 150 grams might not give the exact replication of what you needed, because since you are interested in the quality of roti. Okay, same time, if you are taking like 10 grams measurement, then it's not needed. It's very small, which is wasting your time and energy and effort. Okay, so the scale of scrutiny usually should match with your process needs. Okay, so in general, when we are talking about process, again going back to wheat flour milling, we will be manufacturing tons and tons of wheat flour, right? That's in the process scale, but for analysis we might bring some in sample scale, right? Tens of kilograms or a small tote bag, right? But when we use for testing, we take very small amount, right? For example, particle size, like you take 2 grams from that tens of kilograms, right? So we always have to subdivide the sample, right? So from tens of kilograms to couple of grams, right? So the tens of kilograms is the subsample that you collected from the large process, but still you have to subdivide for matching up with your scale of measurement, right? So always we'll have to subdivide the sample, right? So can you guys give some example of instruments that we use for subdividing, at least for grains and food? So when you take subsample of rice, sample of rice, how do you subdivide? Okay, no, do you use any instruments to subdivide the sample? No, okay. Anyone? Okay. Okay. Yeah, okay. It's around like scoop, right? Yeah, you're scooping out samples, subsamples, right? Any other instrument that you would have seen? No? What's that? Sieve shaker, that's not for subsampling, but it's for mostly size measurement. Okay? At least for the people from who are studying here, you should take a walk around your labs, okay, very frequently. Okay, there should be a Bonnier divider at least. Any of you seen a Bonnier divider that's used for grains? It should be in the grain lab or whatever properties lab. It should be at least. Okay. It's very common. We'll talk about and again. Sample size reduction again. Scoop sampling is okay if you are talking about or if you are dealing with cohesive powders. If it's cohesive, the chances of segregation will be low, so you can just scoop a sample. So, but again, there will be lots of segregation if it's even mildly free flowing. Okay, if it's free flowing, then there will be lots of segregation. Okay. So one of the, if you do not have any instruments, then one of the method that we suggest is cone and quarter. Okay. For example, you are bringing 10 kilogram of sample and you wanted 100 grams. Okay, so you can make them into a cone and then subdivide the cone into 4 equal parts, throw 2 of them and mix the other 2, then keep on subdividing till you get the amount of sample that you wanted. Okay, so cone and quartering again, when the material is flowing into a pile, it would have segregated equally into different sections within the pile, and then it would have segregated from bottom to top. So that's why you divide them into 4 and then throw 2 of them out and then mix the other 2 and then keep on subdividing. Okay, that's again one suggested method. Again, there will be lots of operator bias too, right? How you make the cone, right? For example, in agriculture, if you are piling lots of soil, so how will you pile the soil? So and type of soil too, the type method of piling will define how you cone and quarter, right? Table rifler and chute rifler are very common. Table rifler again, it's again very simple system. You may have one in here too, or at least in mechanical engineering or chemical engineering here at IIT. So very commonly used. So you make the powder flow through different streams. So the powder will be flowing into different streams and collected into different multiple substreams. Okay, so it kind of gets the essence of segregated mix within that powder. Okay, very similar principle like chute rifler. So this is more kind of automated, maybe automated, but again chute rifler, there will be multiple streams. In a table rifler, the number of streams might be limited, but in chute rifler there will be multiple smaller streams that collects different streams of powders when it's flowing down. Okay, and then mix them together and makes into a subsample that you can use. Okay, so this is the same principle that you might have seen. Again, you should have one in your food engineering lab. Same principle like a chute rifler and a Bonnier divider. There will be smaller chutes inside the divider, and when the grains or any powder flows through it, those different chutes collects different sections of the flowing material and mix half of that flow into one product, one stream, and then half of them into one stream. Okay, so you keep on subdividing till you get the amount of sample that you needed for your characterization. Okay. So spinning rifler is the most accurate or more appropriate. Okay, I'm using a very old picture here, but there are more advanced spinning or much better looking spinning refillers in market nowadays. Okay, so the same operation is simple. So you make the powder flow through small, a chute or rifle system, and then it flows equally into those smaller compartments. Okay, it flows equally into those smaller compartments. So you are collecting, and these compartments will be rotating. They are not stagnant. It rotates at one constant RPM. So those powders are collected in individual compartments at multiple times, and then you take those subsamples. Okay. Again, for most of the powders, we'll have to optimize the RPM before we subsample that, to give a better better result. Yeah, vibratory feeders are common. The powders is not very free flowing. Then to make them flow freely, you give some vibration on the feeding chute so that the material is flowing uniformly. Okay. So again, as I said, most commonly, the rotary rifler gives a very good result with very low standard deviation of the measurements from the sample. Okay. You can see cone and quartering gives a large variation, but still, if you do not have any other instrument, you can still use cone and quartering method. Okay. Yeah, again, I'll skip these advantages, disadvantages. Again, there's one detailed study. You can, it's free to download. If you go into NIST website and or Google Jilla Venkatesa et al. For sampling protocol, you can download the document. So subsampling, we always suggest, for anyone going into the industry, one of the first things they will have to do is develop a sampling protocol. Most of the industry may not have a sampling protocol. How you sample powders. Okay. So this again, I'm not going into the study, but what they did was they collected lots of samples and subsamples and mixed them together. Collected and repeated those multiple times, and to find out an appropriate sampling procedure to minimize the errors, or find a sampling procedure with low standard deviation. Okay. So again, I'll not go into the detail, but again, it's freely available in the web. You can just Google and see those details. Okay. Any questions?
You have to mix the sample from that particular compartment.
No, you don't have to. So you can keep on subsampling. So this is not sampling, this is sample dividing. After you already sample, for example, you have 100 gram of sample, you want 2 gram from 100 gram for particle size. Then you use that spinning rifle till you get 2 grams. Okay. So this is subsampling. You don't have to do any further division. Okay. Is that clear? Is that clear, or is that okay? Any other questions? Yeah, go.
Sir, is it like dilution we will in laboratory?
What is that?
Dilution.
Dilution. Yeah.
So is it similar like dilution?
Dilution, you are reducing the concentration, right? So you are like, you are not diluting. You are just, for example, if you take, in sugar solution, if you are adding like 100.
Like for finding the number of micro where in the sample, so we dilute it to reduce the sample size.
No, this is, so for example, if you have some, before diluting, if you have like some microbes population, right? So you are dividing those population equally so that, all the microbes are same in all the, whatever subdivision. You are not diluting. It's like subdividing. Okay. Any other questions? No other questions? Are tired? You need a break? Okay, so let's take 5 minutes break. Okay. Is that too short, 5 minutes, or too long? 5 minutes okay? Okay. So let's take 5 minutes break, hopefully before, what time is lunch? 1? 1:30, okay. So hopefully we'll be done with sampling before lunch, and then after lunch we'll talk about particle size. Okay. So we'll do some calculations now when you come back. Okay. So far is it okay? Are we learning something new? Okay. Go ahead. Yeah. Okay. So it's the again t distribution bell curve, so you'll have two tails. Okay. Okay, so first thing, for example, okay, so you all have your calculators ready? Okay, so we are collecting 8 samples from a powder to determine its bulk density. Okay, we collected 8 samples. Okay, so determine, first we are not calculating the number of samples, but we are calculating the interval with which in the mean bulk density lies with a confidence level of 95%. So whatever 8 samples that you have collected, you have to be sure that it's accurate representation of the bulk sample. Okay. Okay, so how do we do that? So again, I have the answer. So first thing is you will have to calculate the mean, right? So you know the mean. To calculate the mean, okay, you'll have to calculate the average value first, right? So from the 8 samples, okay, then you get the mean, and then again from t values from the t table, students distribution, t test distribution table. Yes, again, S is the standard deviation that you calculate, again from the given values. N is, you know the number of samples, that's a number of samples. Then if you plug in all those, you will you get the distribution with the 95% confidence. Again, I have values in 3 slides, so you don't have to calculate, but we will do lots of calculations, okay, at least some, okay. So it gives value of about 1.21 plus or minus, it gives about 95% confidence interval of your subsampling. Or subsampling, the measurements are within this range. Okay. Okay. Using statistics, again, as said, it can give some closest approximation. Okay. So again, from the values, can we use them to calculate the number of samples needed to determine the mean? Again, that should give a value of that subsamples that you are collecting for density within 0.01 gram per cc. So whenever you collect some samples, that should give the mean, the standard deviation should be within 0.01 gram per cc. So for that, values with a confidence interval of 95%. So now you are not collecting 8 samples, but you are just using, the standard deviation, okay, or the confidence that you wanted to get to this close, or very approximate characterization, but we need to get the total number of samples that are needed, okay, to get this very, exact value or very, accurate value of density. Okay. So again, it's the same, principle. The t distribution, t test values, standard deviation. The mean and average. Okay. So use that. You calculate. Again, it comes to about 18 samples. Okay. So if you collect about, for this example, okay, if you collect about 18 samples, these all are direct plugging in numbers. Okay. Plug in the numbers, you get the values. Okay. So, but again, so if you wanted to collect them again, to get the number of samples, it's kind of, you'll have to do some arbitrary calculation. So you'll have to assume a number of samples to start with. Okay. Because no one asked me that, right? So for t value, you need n value, right? So to get the t value from t distribution value, you need to know the number of samples, right? So without knowing the number of samples, you cannot get t value, right? So we have to start somewhere, with some assumed n, okay? So you keep on calculating, for the confidence interval, okay, or the closest accuracy value at one point, with increase in n, the n prime or your actual value wouldn't change. Okay. So at that point, you can take the lowest number or the lowest n value as the number of samples that you are needed to get, accurate value of density, at least for this example. Okay, is that clear? So you start somewhere, okay, with some assumed n value. So you need n value to get t value, right? So you start somewhere and then you keep on increasing, keep on decreasing. Then at one point, this n prime wouldn't change. So that point when it plateaus, you take that value as the minimum number of sample needed for characterizing to get good, good close approximation of the density within that confidence interval. Okay. Just pure, using statistics, it's very simple. Okay, as I said, it might not give the exact, calculation, but it gives a close approximation. Okay. So using those, again, different statistical principle, you can calculate the total measured variance. We talked about these, right? So true variance within the sample, there will be variance from sampling itself, and there will be variance from the instrument that we use for characterization, right? So ideally, the sampling and analysis variance should be low or should be easily controlled or should be zero. Only you're characterizing the true variance within the sample, but it doesn't happen all the time, right? But again, you can use those variance equations to calculate all these, total variance or measured variance from all these variance values. Again, I'm not going into that. Again, you can use simple variance calculation, variance equations, to use the, or to calculate the ideal minimum variance that you wanted to have when you are subsampling from the bulk powders. Okay. And we talked about sampling protocol, right? So initially when you develop a sampling protocol, so first you should know the characteristics of the material itself. Okay, we talked about free flowing and cohesive material, right? So first we should know the powder characteristics. If it's cohesive, very cohesive, like cake material, then you can just use a scoop for subsampling. Okay, it doesn't affect your characterization much. But if it's free flowing like rice grains, corn, cereal grains, then you will definitely need an appropriate sampling procedure, okay, that reflects their flow behavior or flowing characteristics. Because when it's flowing, they segregate, right? When it's free flowing, they segregate a lot. So again, determine the quantity of sample needed. Again, identify sampling technique, sample tool. Most often, in current industry scenario, it's limited by the system we have in the industry. It's not that we buy a new system. Usually, you might go and work for an industry, and your manager might say, "Oh, just use the scoop and get sample," right? So if they don't have any other advanced technique, but now you know why sampling is important, right? So you'll have to have a good sampling protocol. Again, prepare subsamples. Conducting homogeneity test, if you can at least, do some homogeneity test where the samples are mixed, uniformly, equally within the bulk, then it gives more, again, more representative characteristics of the materials, right? If it's not homogeneous, if you see lots of variation, then you will have to redevelop your sampling protocol. Somewhere, the method or equipment or sampling system that you are using may not be very valuable. Okay. So almost, towards the end of sampling now, very common. That's what it happens. Except maybe in pharmaceutical industry. Pharma, again, as I said, it's low volume, high priced, material, right? But in grain and food, it's like high volume, low priced. So we generally don't care a lot about, subsampling, quality analysis, etc. But, if for example, if you're working in a wheat flour mill, if the baker doesn't complain, okay, or a person who cooks roti or makes roti in home doesn't complain, then the wheat mill, wheat mill engineer doesn't care or doesn't worry about it, right? So it doesn't worry about sampling or process manufacturing, etc. So if there is no problem for the downstream, if no one complains, then why cares or who cares? Okay. Again, that's what happens when you're dealing with like large volume, high volume, low, profit margin, industry like, ag or food, etc. Okay. But when we go, if you're going, by any chance, if you're going to work for a pharmaceutical company, then this will be a big challenge because they have very limited amount of samples to deal with. So then, they should, have a sampling protocol, sampling, method, etc. Okay. Again, poor communication. Again, if you are working on the floor in the process, you may not, know what the, R&D group wants, right? So they might have different requirement than what you can do in the floor during manufacturing, and vice versa, right? So if, you should have a good, communication with other groups that are involved in the, process manufacturing, from R&D till planning, etc. Okay. And again, better sampling. So proper sampling, and as we saw, it's not very difficult to establish. It's very easy. You should know some statistics. You should have some, some sampling equipment. Okay, simple sampling equipment. That's what you need to, establish a sampling, protocol. Okay, it's very easy to develop and very easy to implement. Okay. So keep in mind again, a couple of golden, we talked about the golden rules of sampling, right? The powder should be in motion, and then collect from the whole stream of flowing powder at, many periods, many short duration than one bulk, subsample. Okay. Again, if you are using some sampling devices, mainly, understand the limitations. I showed one picture of pharmaceutical powders, right, with an N sampler. So, if that is like periodically segregating powder, or if you are, putting different powders in batches, then an N sampler might work better than a thief sampler with multiple pockets or multiple openings. Okay. So understand your process and understand your device that you use for sampling very well, so that you can, so that you can develop, good sampling protocol. Again, for subsampling, we always suggest, the use of spinning rifflers. So you would have seen from that example, right, the variation from spinning riffler will be very low compared with other, subsampling methods. Okay. I think that's my last slide. Any questions? Someone was happy when I said last slide, But again, if you are interested, there are tons of, standards that you can follow. ASTM has many standards for sampling, British standards, ISO. You should be able to, I'm not sure if your library has access, but, these standards may not be free to download, but if your library has access, you can, download and use it. These are some of the references that I used in this lecture. Okay. Okay. Any questions? That ends our sampling part. Okay.
What if the statistical analysis gives us a large value of number for the samples, and we are dealing with the high value component or high value material? Can we reduce the number of samples?
Yeah. So in general, it wouldn't give large. So the large the number n, goes up when you tighten the standard deviation accuracy. So if it's like, in the slide example that I gave, 0.01 gram per cc, right? So it's very tight. So if you are increasing your accuracy, like, the number of samples needed will also go up. So you'll have to compromise somewhere, one, compromise in the accuracy or compromise in the number of samples. Okay. Any questions? So I'm making it difficult. I'm moving a lot. Is it okay? Any other questions? Come on, you guys are like hungry? How many of you are hungry? No one? No one is hungry? So the snack that they gave this morning was good? So no one is hungry? So we'll have a 1, right? Up to 1? Okay. So I'll start the particle size stuff. I'll cover a little bit and then okay, so let's talk about particle size. Okay. Is that okay? You guys ready? So okay, and again I know talking about particle size and lunch will be difficult, right? So when you eat lunch, make sure to notice what type of different particle sizes that you're eating. Okay. So what variation in particle size that you can observe. Okay. So particle size is very important, right? So for any process development, process streams, particle size characterization is important. Again, unfortunately, we are not dealing with well-defined shapes, right? So for example, if you're talking about spherical particles, cylinder, cuboid, etc., those are well-defined shape, right? So you just need one number to tell the size of that material, right? For example, spherical particle, if you know the radius, then you know the sphere, right? If it's a cylinder, maybe you need 2 dimensions, length and the height and the radius, right? So you have the cylinder dimensions, very uniform, very regular particle, right? Cuboid, if you know the side length, then you know the the size of the material, right? But unfortunately, in ag systems, we are not dealing with regular shapes, right? So you take any kind of agricultural materials, they are never regular shape or regular size, right? Take anything, soil, from soil till any product, their sizes are completely different. We always get a distribution, right? And their shapes are also not uniform. That makes it very complicated to characterize the size, right? So again, just an example of corn kernel here. It's X-ray tomography image of a corn kernel. So I put that in. We use this X-ray CT scanned images to develop corn kernels when we simulate using DEM modeling. So for get the accurate sizes, okay, and shape. So what are some of these size characterization measurement systems that you can think of? Any examples of size measurement techniques? Malvern, laser diffraction, yes, that's very common now, right? Most of the labs will have, most of the industry uses, okay. Any other systems that you can think of? Sieve analysis, very common, right? So that's the most go-to place for size measurement, right? So what are the techniques that you can think of? Okay, scanning, exactly. So microscopy technique, it could be scanning electron, optical, any type of microscopy technique, right? Anything else? What's size exclusion? Okay, see, it's again very similar to micro CT and what is that? It comes in between the what technique is that? So suddenly went blank. Okay, so very similar to optical and right? Optical method, right? Very close to optical method, right? SEC technique. Okay. Well, I think I have a slide on that. Okay. Any other technique? What? Okay, confocal laser, using laser, again, it's a light principle, right? Anything else? I think you almost covered most of the techniques, most common techniques, okay? So how do we measure size? I don't know, many of you would have seen this slide, right? So how do we measure size? Again, this is from Malvan, right? So what do we do is, and it's said, for any, agricultural material or food material, the sizes are not uniform, and then the shapes makes it complicated, right? For measuring the sizes, right? So what do we do is, you take that material and compare with another property, okay? Just to make it as a spherical particle or spherical material, okay? So spherical, again, why we are making it into a sphere? So we just can define using one number for that, particle, size using one number. But for that, getting that spherical size, either, again, we compare with the sphere of same weight, same mass, same sieve aperture, maximum length, minimum length, surface area, volume, etc., right? So for one same particle, how many different sizes you can measure, you can see, right? So the sizes change, or sizes differ, right? So depending on the technique that you use, the size is also not the same, right? So it told SEC or sieve analysis or laser diffraction, right? So the sizes that you measure from these techniques will not be the same, right? So why it's not the same? Because we are using the fundamental principle, a different fundamental principle or different fundamental property to get the size of that material. Okay, so that's again somewhere in the slides I should have that. So when you measure size, make sure you do not compare sizes measured using two different instruments. So you are not comparing apples to apples. If you are comparing with using two different measurements, then the physics that we use to measure is completely different and the sizes are not the same. Okay. So same, the size is also same and also their distribution will also be different. Okay. We will talk about distributions in later part of the class. Okay. But most importantly, what do we how do we characterize sizes? We correlate with the end purpose, end use. Okay. So why do we characterize or why do we measure the size for? Okay. Just as an example, if pneumatic conveying, if you are measuring some size for pneumatic conveying, then again we use the Stokes principle or aerodynamic diameter of the particle when you use for pneumatic calculations or pneumatic systems design calculations. Okay. At the same time, if you are calculating the size of a paint particle, for paints and surface paints, okay, then you wanted to use based on the surface area diameter. Okay. So how much surface area that particle can cover when you are painting. Okay. Same for coating too. If you are coating particle to particle coating, so then you will have to worry about the surface area of the surface area dependent size of the particle. Okay. So you will use the sphere of same surface area to the sphere of your particle and then get the size of that particle. Okay. So we can go on theory for lots of many things, but finally what it comes to is what type of instrument you have in the lab. Okay. If you do not have a laser diffraction, what we do is end up with sieve analysis, right? That's a common, it's not expensive. Just use a stack of sieves and get the the size of the material, right? But now right, you should not use the same sieves for same size for other purposes, right? So when you are measuring, make sure you are measuring the accurate size for the purpose that you wanted to use. Okay. So same, if you are dissolution, mostly again surface area, depending on again the purpose, you will have to use the appropriate size measure. Okay. So again, before going to example again, went through most of these size measurement techniques. Should see. I'm seeing the trying to see the method that you mentioned, SEC. See it here, but I have it somewhere. I forgot the exact physics principle that they use in SEC, but Okay, so again, size measured using different principles. Again, we'll have different measures, so don't compare when you are measuring sizes, measured using two different instruments. Again, most often we use the size to monitor the process change. Okay, so how the size is changing due to some milling process. I'll come back to that in an example, with an example in a minute. And again, in many places, sizes are correlated with the property that we wanted to measure. Okay, so I'll come back to the size measurements on relative. For example, going back to wheat flour milling example. Okay, so what is the size that we talked about? What is the minimum particle size for wheat flour? Yeah, you all have a good memory than me. Okay, 140 microns, right? So that's what when you are measuring the particle size of wheat flour. Okay, so we in general talk about whether the particles are around that 140 micron range. Okay, so if it's above or below, we don't care. We don't quantify that accurately if it's above or below. If it's closer, then again okay, we use that measure. Okay, for again, size is measured and correlated with other properties. Most often when it comes to downstream processing use, we try to correlate with their size and their behavior. Dissolution, in most of you at least would have used fruit powders, right, for making drinks and stuff. So then again you wanted smaller size powders, right, with high surface area per unit gram or per unit volume, so that they dissolve immediately, right. Same thing again for going back to wheat flour example too, we talked about ash, right, ash and its effect on baking quality. So if you wanted to have, if you have ash also, their particle size should be very small, right. If it's very larger in size, then again that will affect its baking properties. Okay, so again, depending on the downstream process, you worry or you care about the type of measure, measurement method, or how accurately you wanted to quantify the size. Okay, so I'll go through some examples. Okay, so why size is important. Okay, so one is when it comes to mixing. Okay, as the picture shows here. Okay, so when you reduce the size of the particle, again when it comes to mixing and blending, you might get a better uniformity in mixing, okay, than in a larger size. Okay, so if you have a larger sized particle, you can see the relative standard deviation of mixing will be high, but if it's small size powder, then your mixing quality might be a little better. Your relative standard deviation will be very low. Okay, will influence blending or mixing. Okay, and then again on flow behavior, right, so how it affects flow. So which particle will flow better, small particles or large particles? Small particles. Okay, so one more option, large particles. Okay, you can go wrong only once, right, small or large. Okay, so usually the larger particles will have a better flow in general. Again, it's not true all the time, but in general will have the cohesive surface forces will be low when it comes to large particles, and then many of the larger particles will have a again inertial force that is high. Okay. So if you have high inertial force and less cohesive surface force, then the flow behavior will be better. Okay. So again, I'm not going to do this, but we will talk about bond number later, little later. Okay. So again, bond number, you would have learned about bond number, right? So gives a ratio of at least, except the agriculture students, maybe ag engineering students, you would have learned. So it's a ratio of surface force to inertial force. Okay. So as the bond number increases, the cohesive surface forces becomes relatively more important. Okay. That means if the cohesive forces are high, then the flow will be challenging, flow will be difficult. So if the particles are larger, then the cohesive forces will be low, and then they flow better. Okay. And just one other quick example here. some of you know Hausner ratio, flow function, etc., right? So these, again, we'll talk about these when we talk about powder flow, but just giving a quick, background. Hausner ratio gives some indication of powder flow behavior. So with increase in particle size, the flowability goes up, or the flow behavior goes, becomes better. Same thing, flow function will also improve if the particle size goes up. Okay. Any of you measured flow properties using shear cells or any other instruments? No? Okay, so again, oops, what did I do? Okay. So dissolution time, we talked about, dissolution time, right? So you all know about, most of you at least know about Fick's law, right? So Fick's law, again, that, characterizes the dissolution rate, and again, you can see it mostly dependent on the surface area, right? So surface area that comes from the radius of the particle, okay? So again, if the radius of particle is smaller, okay, the surface area per unit volume is higher, then the dissolution rate will also be higher. Okay. This might be a little difficult for you to see, but again, these graphs shows the dissolution behavior of different powders starting from large particle size, and the lines on the top are smaller particle sizes. Okay, so you can see the nutrient release or drug release is very high or quicker for particles of smaller size. Okay. For larger particles, the nutrient release is much slower. Okay. So how does it affect your particle design or granular material design? For example, you would have learned, what is that tablet name? Yeah, Gelusil. It's called Tums in the US. How many of you would have used Gelusil, right? It's a tablet for if your tummy, stomach ache, if you ate more, if you have acidity problem. What is the tablet that you use? Is it Gelusil? No? Is it a tablet? Yeah, I heard. What's that? Day1. Oh, yeah, Day1. It's a tablet form, right? So yeah, we call it Tums in the US. Okay. So when you just I'm giving an example. So if you ate a lot, okay, and then if your tummy hurts, so you want immediate relief, right? So then you take, you consume a Day1 or want some tablet, right? So Day1 or any those kind of tablets will be of high porosity will be very high. So when you consume that tablet, you wanted them to dissolve immediately, right? So you want to get immediate relief, right? But at the same time, if you are having a fever, right? So fever, again, it's a long process, right? So it doesn't go off for like 3-4 days, right? So you want continued supply of drugs, right, or medicine. So those tablets usually come in like very compacted form, right, or in capsules, like very, solid capsules. So that releases nutrients very slowly. Their particle characteristics will be completely different than the particle characteristics that you see in a Gelusil. Okay? So those, again, going back, the particle size, those particle characteristics, we use them to design our, products. Okay? So if you take any products, most of the time we use their, fundamental properties to, adjust their process performance. Okay? Same for fertilizers, or soil, anything. Okay? Fluidization, again, we talked about briefly, right? So fluidization, again, depends on the density, right? So the relationship between the density and the particle size, their fluidization behavior will also be different. So ideally, we want in this area where we can easily fluidize them, or we can easily convey them using the pneumatic process. Okay, so the particle size, density relation should be, around this area. But if the particles are of very small size, then they will be very cohesive and it will be very difficult to fluidize them. Okay. Or if they are very large in size, then they become spoutable, not fluidizable. Okay. You all know about popcorn, right? How the popcorn machine works. So mostly it's spouted bed rather than a fluidized bed, right? So you might end up with a spoutable bed than a pneumatic conveying system. So compact strength, again, we will talk about tensile strength, etc. But with the increase in particle size, the compact strength goes down. So if you are making any, food powder tablets, like nowadays there have been lots of work going on making, dairy powder compacts, making well mixed dairy powder compacts so that they dissolve quickly. So if you are in the future, if you are going to work in that industry, make sure your particle sizes are small so that they will have good compact strength, so that they won't break during handling process. Okay. Dust explosion, again, if the particle sizes are small, the energy released will be much quicker, and then the explosion severity will be higher too. Okay, if the particle sizes are small. I'm not sure. Any of you working on 3D printing? You are. What are you printing? Which powder? You can sit.
Printing are based on what we are first we prepare for ink.
Okay.
After that we have to work to done this type of part we have to design on AutoCAD or something like that.
Oh, okay.
After that we have to design.
Okay. Okay. So it's just an example here, how particle size. This is, printed spinach, I don't know how they are very, I don't know, how many of you all know spinach, right? The green leaf vegetables, okay. Okay, so in this example you can see, I was thinking, why do someone wanted to print spinach, okay. Okay, so it's, I know for kids and young people, spinach is not a favorite one, right? It's not a favorite vegetable, right? But so here, again, larger particles had a better shape or better stability. It's not about the shape, better stability for the printed, 3D printed material or spinach than, when they extruded with smaller particles of spinach. Okay. So again, depending on the process, these properties change. Okay. And other effect segregation, definitely, right? If you have a mix of larger and small particle, you will have a big effect on segregation. Even if it's smaller particles too, if it differs in chemical composition, then you might see some difference in the property after handling. That means it segregates a lot. Again, hydrodynamic effect, inertia, etc. Fracture strength too. If in general, larger particle will have a more, higher chance for fracture initiation sites, or where you will see more stress concentrations that leads to breakage of particles. So again, depend on the size. Okay, so this is again, we will talk about that. In general, again, this slide is from Malman. We use sieve analysis for larger particles and microscopy techniques for smaller particles, right? That's the range commonly we use, but again, we talked about the type of measurements and their physics, right? So again, do you know what principles sieve analysis uses to measure the particle size? So what are we using? What property of the material are we using to get the particle size? Spherical diameter, no, not. What is the property of the material that we are using when you use a sieve analysis to get the size? Not major diameter. So that's again that you both talked about the sieve opening, right? So sieve opening will again major diameter, not always, right? So if the particle is slanted, it can go in any orientation, right? We'll talk about that in a minute. But how do we measure particle size using sieve analysis? What do we do? Can anyone explain? What do we do? What's that?
Volume fraction.
Volume fraction, no, that's in laser diffraction we use volume. Okay, now we are close. Okay, we don't use volume. So what else we use for sieve analysis? What's that? No, very close, not that. What's that? Mass fraction, mass, right? So weight. So based on weight, so particle size is based on the weight, right? So amount of samples that we, that's collected in each sieve, that's a property that we use to get the size, right? We use we calculate the arithmetic mean diameter from the amount of samples we see, collect in, different sieves. Okay. So that's again, that uses weight. Sedimentation uses again Stokes principle, right? Aerodynamic, property. Yeah, SEC, it's very small particle again. Optical, imaging again for two-dimensional orientations. Laser diffraction again, optical influence, or light influence on, particles, right? So we use different principles, but again, the measurement techniques, they all differ on the degree of resolution, right? So if you go, to a high-end instrument, then the degree of resolution will be much better, right, than a sieve analysis. Okay. Again, as we talked about sieve analysis, the particle orientation may not be constant. So you always get a mix of, you take sample from, that's collected in each sieve, you still get a distribution, within that sample. Okay. Again, the principles, that different systems or different techniques uses are not the same, right? That depends on the type of instrument that you used and type of instrument that we use, and the type of distribution that we get are also not the same, right? So there are 3 different types of distribution that we normally characterize, the size distribution of powders that we characterize from the measurement techniques. Okay. Can anyone know? Can anyone give the 3 distributions that we characterize? Particle size distribution. So at least 2 of them you gave, but you just have to say them. So volume based distribution. Okay. One is volume based distribution, one is mass based distribution, right? So what is the third? Any guess? Surface area, yeah. So we don't commonly use, we can use surface area too. What's that? Surface? Yeah, surface volume, yeah. So that's again surface area, but there is another basic. These are from other properties, right? But volume, weight and number based distribution are the 3 common distribution that we use in different measurement techniques. So number based distributions are, if you are using any microscopy technique, we use this number based distribution because the size or the characteristics will depend on the number of particles that you are using to measure, right? Any of you use microscopy technique for measuring size? No? No one? So there is Malvern, G3ID that uses optical principle, or you can use any optical microscopes too. Okay. So put some particles in the slide and then you measure the size. Okay. But again, if you increase the number of particles that you are spreading on the slide, then your values will also be different. Okay. So the distribution is based on number. So based on the number of particles we use to characterize, then the distribution will also change. Okay. But for laser diffraction, it uses volume. Okay. But for sieve analysis, it uses weight based distribution. Okay. So again, we'll talk more about those things when we come back in the afternoon, okay, for lunch. First we'll talk about microscopy and then we'll go on to some of the other, common techniques. I will not be covering all the techniques, but some of them, okay. Any other any questions before you guys leave for lunch? No? Okay. Yeah, lunch break, yeah. I don't know. 2:30? 2:30. Or maybe, you know, you can check with Dr. Murthy. Yes, I don't know. You ask him. Yes, I'm leaving lunch early, right? 1 o'clock. Okay. So where you all will have lunch? So is lunch arranged? No? Lunch is arranged? No. But we have some outside people too, right? Where they will have lunch? Private school. Okay. Okay. Okay, doctor.